Cool. Excellent. All right. We'll give one more minute for anybody else to join us, and then we'll start.
I have all of it in my office. I thought Gina told everybody while I was out last week. I'm not heard anything. I know we talked maybe a month or so ago. I thought I would be listening. Yeah, exactly. So it's probably up to you. So you can call first dibs on the low health thing. I think some of it is Bob and I weren't sure because we had another office. Or you don't anymore. Okay. So I would say it depends. On the system.
Excellent. Welcome to everybody who's joining us online.
Okay.
Here.
Okay. So if you
And for those of you online, you should be seeing the front page of the talk now. If you're not, chirp in. All right. Hey, welcome everybody. Thank you for coming to the last one of these talks for the season. Is there anybody here who hasn't been to any of the previous propensity scores and related methods talks? Okay, good. Well, welcome. Thank you. Yeah, thank you for coming. This actually ends up being a nice talk in the sense that you'll get to see a concrete example, and I'll just make sure to review some of the ideas and materials that I'd otherwise blast through. I'd like to acknowledge my co-authors on this example, Christiane, who's down at the end of the table, who I think will appreciate this example that we're going to go through today, along with Lucy, who did a lot of the heavy lifting on this code, and Amber, Carlos, Adriana, Harley, Harvey, and Marie. These are preliminary results, so please don't distribute or discuss the results until hopefully soon you see them in press, and there's no COIs with the research that we're doing. So what we're going to do is we're going to look at metformin versus sulfonylurea, a weighted analysis. For those of you who got to go to this particular talk, will be an example that we started a while back. And then we're going to look at metformin versus TZD, trying to do essentially a parallel analysis to what we just did with the metformin versus sulfonylureas. And we're going to see what goes wrong. We're going to see that the MET versus TZD doesn't work, and then we're going to look at how to fix it. As always, discussions and questions are welcome throughout. We like to keep this informal. So we and others have shown that metformin is preferable over sulfonylureas for incident antidiabetic monotherapy, i.e. the first-line therapy. Sulfonylureas have a worse risk profile for all-cause mortality, CVD, CKD, weight gain, durability of A1C control. So we expected that fall will have a greater risk of congestive heart failure, but the evidence needs to be nailed down. We have a cohort of around 350,000 active incident anti-DM medication users starting therapy between 2002 and 2008 with follow-up through 2011. And there's a technicality there that we can get an incident case later than 2008. If there's curiosity, I'll get into that. We require that they be active EHR users, i.e. that they have some sort of health encounter every 180 days for the last 2 years. That means we know that they're in the system. They need to be incident users, that is they have to have no anti-diabetic meds available for the last 180 days when we see them. And a key point is 2002 to 2008 are good years to study when comparing metformin to sulfonylureas because it wasn't established which was going to be the better medication. In fact, in our cohort early on, about 60% of the incident fills are sulfonylureas. And over that time period, by the end, it's about 60% are metformin. So it's pretty close to a coin toss what people are getting. So that heterogeneity in practice really makes a good study ground. Follow-up begins 180 days after initiation. This focuses on persistent as opposed to the acute effects of the medication. It eliminates high exposure misclassification that can occur in those first 6 months. And we're going to be studying those acute effects separately. So we have certain key exclusions in order to filter down the data set. Things like if date of birth doesn't exist, if they're not 18 yet, if they have a creatinine value that contraindicates metformin. That's both for the metformin users and the sulfonylurea users. And so we have people who are equally eligible for those medications and so on. So we end up with about 66,000 sulfonylurea users versus 108,000 metformin users. And Christiane, if these numbers don't look exactly right to you, it's because we've updated them. Exactly. This was version like 21 versus 42. So CHF is our primary outcome. It's the date of hospital admission hitting on an ICD-9 code in the primary position or a hit on a DRG code. Our exposure is what we call PER 90, meaning we require people stay persistent on their medication therapy, so they can't fill a different anti-diabetic medication, and they can't go for more than 90 days without their pills in hand, without any pills in hand of their med. And then we do a bunch of sensitivity analyses, which we won't worry about today, but we include a secondary version of the outcome that includes ED visit hits. We vary this idea of persistence, for example, not requiring any persistence at all on the medication, and a number of other analyses to show consistency and robustness to the choices that we make along the line. The raw event rates in this version were around 39 per 100,000 person years for SOL and 16 for MET. So a raw hazard ratio, in our raw hazard ratio of 2.4. But this is biased, and we can prove that it's biased because we can just look at the distribution. We see that among our 66,000 SOL users, our mean age was 68 versus only 64 years in our MET users. They had a higher prevalence of CHF history, 10% versus 4%, a higher prevalence of CVD history, 32% versus 25%. So pretty much along the lines, things that we would think would be predictive of CHF are looking worse in the SOL group versus the MET group, with the exception of, say, LDL, which was pretty balanced on average, though not observed as frequently in the SOL group. That LDL was missing 27% versus 22%. These covariates are selected from 45 covariates that we adjust for. One of the key things that we've harped on over these seminars is the propensity score is only as good as what you put into it. And so if these were the only variables we have, our propensity score wouldn't be very impressive because there's plenty of confounders that we wouldn't be controlling for. So I'm just going to highlight some, but know that there's much more in there. There's a nice tool, for those who haven't gotten to see this particular talk, there's a nice way of getting a sense of the imbalance in a standardized form for the different variables. And we use a special standardized difference formula, which looks at that mean difference, kind of like we saw on the table above, but then standardizes it based on some sort of pooled standard deviation. Now, if we look at Rosenbaum, the formal way to do this is to take the standard deviation within each group, square it, and take the mean, essentially, like the average of the sample variances, and then take the square root of that as our common standard deviation between the two groups. This is a little different. Notice there's no n's in here, and so we're not trying to, we're essentially trying to get rid of the weighting by the sample size. So if one sample size is much bigger than the other, rather than letting that dominate the variance estimate, we just give them equal weight. As done in practice, and by practice I mean what you get done via R packages, you'll see many variations of this. So not all R packages do this exact thing. And it turns out not to matter too much, but the most formal way to do it is to take this even weighting of the standard deviations and to use just the standard deviations from the unmatched cohort, rather than letting the standard, or unmatched or unweighted cohort, rather than changing these standard deviations once we do the matching or weighting. The reason for that is to not penalize yourself by reducing the standard deviation via, say, matching or weighting, and to make it look like you're actually things are getting worse when really you just decrease the variance. A rule of thumb out there is greater than 10 is not great, and greater than 20. And sometimes people multiply these by 100 to put them in percents. We prefer the decimals. And so greater than 0.1 is really not great, and greater than 0.2 is really not good. So we see in terms of age, 0.37, CHF history and CVD history of 0.24 and 0.16. These are really looking pretty bad, with the exception of LDL. And not terrible, but not good in terms of LDL missing. So how can we compensate for this? How can we do something using a propensity score to try to get us to a cohort that compensates for this bias? Well, our propensity score is just our probability of being exposed given our covariates, and we'll just use the symbol E or E of X here throughout the notation to denote that propensity score, that probability of being exposed. And you can measure this via logistic regression or some other, any sort of regression model that will give you those probabilities. And so if we look at our MET versus SOL distribution of propensity scores, this is what they look like for MET versus SOL. And so we do see a bit of a prediction for metformin here coming on. There's a definite difference there. So what can we do with that propensity score? Well, we can match on it. That's probably what most of you have coming here for the first time have heard of. You can also weight by it, and we'll emphasize that a lot in a bit. You can stratify by it. This is what really was originally done with propensity scores, and that was a bit for computational convenience. You can think theoretically how stratifying is always potentially going to leave some residual confounding, because within a given strata, you're not going to have a perfect balance within that stratum. And so the big selling point of stratification was that something like stratifying on quintiles would remove 80% of the bias. And at the time, I was like, great, we're removing 80% of the bias. But now we're much more ambitious in terms of how we want our methods to perform. And finally, you can adjust by it. That's something I will rail against at some point in the future. I'm not a fan of that particular approach. And lastly, I just put a reminder that depending on your data set, if your data set's not very big or doesn't have a lot to work with, it's possible the best you might be able to do is just pick a small number of covariates and adjust by them. There may just be limitations to the data set that have to be respected. So let's emphasize weighting for the rest of this talk. What you do with propensity score weighting is you create a pseudo cohort by weighting the whole cohort by, and here I'm going to jump straight to the stabilized or ATT weight, by the probability of being exposed divided by the probability of being exposed to whatever you were actually exposed to. So the say probability of metformin divided by the probability of being metformin if you're a metformin user, or the probability of sulfonylurea if you're a sulfonylurea user. So these are called the stabilized weights. If you ignore this numerator for the moment, if you just put a 1 in here, that's the typical ATE weight, where it's just 1 over the probability of getting what you got. That's generally what is done, and what that does is that transforms the ATE weight is going to transform both the metformin users and the sulfonylurea users to look like the combined population. So if you put all the MET users and all the SOL users together and just created the distribution of age and the prevalence of CHF and prevalence of CVD and so on, those 1 over probability of getting what you got weights are going to shift the covariate space for both metformin users and sulfonylurea users, so both of them look like what they look like when they're meshed together. And so it's going to create a pseudo cohort, really pseudo cohorts, that each have covariate distributions that look like the combined sample. Now what we do by stabilizing these weights is we put the probability of metformin in the numerator for everybody. And so for the metformin users, it's just going to be the probability of metformin divided by the probability of metformin. That's going to be 1. So what's going to happen to the covariate distribution for metformin users? Nothing. So they're going to stay exactly the same. They all got a weight of 1. But the sulfonylurea users are now going to have a weight that's proportional to the metformin probability for people with the same covariate. And consequently, it's going to shift the sulfonylurea distribution to look like that of the metformin users. And we'll get to see a concrete example in a second. So here's our pre-weighting covariates that we're focusing in on. You'll remember that we had our age difference of 68 versus 64, 10 versus 4 CHF history, and so on. And we had our some fairly bad standardized differences. After weighting with the metformin stabilized weights, note metformin doesn't change at all. All of these values stayed right where they were, but the sulfonylurea users shift to where the metformin users are. And our standardized differences all go to 0 to at least 2 decimal places. The sum of weights for the sulfonylurea users is going to equal approximately the number of metformin users, to give you a little bit of an intuition of what's going on. Because we're essentially scaling up the sulfonylurea users in order to match the metformin user distribution.
Yeah, I was going to explain more than others.
Yes, in fact, yeah, in fact, I'll even jump back here.
I was actually going to ask you that your N looks like it didn't change, but I think that might be a typo because the N should change.
For the MET users, it won't change. For the SOL users, yes, that's absolutely right. So, so Christiane's point is this N is still just number of subjects, but some of these subjects are getting a weight of 3, and some of them are getting a weight of 1/3. Okay. And so the sum of these weights is going to be around 108,000. It won't be exactly that, but it'll be close.
It would be like putting in 3 SOL users who are age 50 and a third of a SOL user who was age 70. Yeah. And in the end, when you average them all out, the age would probably be close to 64.
Exactly. Right.
And
oh, yeah, go ahead.
So here, the standard difference formula here you use
the X1 bar and X2 bar is weighted mean?
Yes.
But the standard deviation X1 and X2 actually come from the original data set, not weighted version.
Yes, the best way to do it. So the best way to do it is the X1 and X1 bar and X2 bar are just the weighted differences, and then the standard deviation. Weighted mean difference. Thank you.
And then standard deviation basically the same as the previous.
Exactly. That's the best way to do it. The Table 1 package that I like doesn't do exactly that. The Table 1, there's a package just called Table 1, which I'm rather fond of as a package. It doesn't do exactly that. It actually lets the standardized deviation change. Lets the standard, so it would use the weighted standardized weighted standard deviations. It ends up not making too big of a difference when things are working well. So if things are working well, it ends up not making too big of a difference.
But your preference is that use the original standard deviation.
Yeah, that's my preference.
Not really much different.
Exactly, exactly. Especially when it's working well, you're getting zeros across the board. Doesn't matter what you're dividing.
Right. Very similar. Doesn't matter.
Why, can I ask you,
Oh yes.
why does the weight of the sulfonylurea set equal the original 10 of that group? Why does it equal the other group?
Like why does it end up being so why did, like if we summed up those weights, why would we get 108,000 instead of 66,000?
Right.
One way to think about it is imagine all of our covariates had no predictive power at all in terms of exposure, and so the beta propensity score model were 0 for all of these things. Then the only thing that would come up is just the intercept. And so that model would estimate just the intercept, which would reflect nothing more than the probability of being met versus stall, which is a little bit greater than met. And so everybody, all the stall users would get a probability of like 1.25 or 1.3, about 1.3. And so every stall user would get a weight of 1.3, and it would sum up to 108. Good.
Because even if you hadn't done that, wouldn't you still fix your bias?
And so
like if you had your intercept was
good. And so if there's no predictive power in these, that would mean that all of our confounders are perfectly balanced to begin with. In which case we wouldn't have a bias problem, and so we'd be bias free, at least in terms of the observed covariates. And so let's look at focus in on the hazard ratios. So the pre-weighting hazard ratio for sol versus met was 2.4, whereas but we claimed that was biased, and the post-weighting version is smaller, as we'd anticipate, because remember all the bias was pointing in the direction of greater CHF for sol. So now we have a hazard ratio of about 1.3 with a nice, fairly tight confidence interval. So after removing the bias due to covariate imbalance, we have a good estimate of the sol versus met effect. Now let's try the same thing for TZD versus met. Now note the in 2003 in Circulation, the American Heart Association and the American Diabetes Association published a consensus statement on TZD use, focusing in on pioglitazone and rosiglitazone, and fluid retention and congestive heart failure. And the conclusion from that statement was both patients and healthcare providers should be cognizant of the risk of CHF when TZDs are used in patients with type 2 diabetes. So they didn't go as far as saying don't do this, but they essentially said there's a heads up. There's a heads up that we have some concern at this point based on the evidence that's being accumulated so far. And at that time there were some RCTs going on, as well as additional information being pulled together. And really towards the end of our recruitment period, sort of around 2007, 2008, you'd say that it was, there was genuine concern about TZD CHF first.
I'm trying to think of the Steve Nissen article, which was a meta-analysis of all the clinical trials, found the heart failure, CVD risk in Rosie. I want to say that's around 2004-ish.
Okay.
But easily the kind of clinician knew that TZDs could exacerbate heart failure among those who had heart failure by, it was relatively early on in their release, so 2001, 2002. And then 2003, there was a statement that says, hey, you guys should know this happened. But then 2005-06 was really when everything plummeted as far as prescribing of it.
So after applying the similar inclusion exclusion criteria as we did for SOL, we get about 7,000 TZD users versus about 140 metformin users, 140,000 metformin users. And I'm looking at some of the same covariates early on, and then I changed some of the later ones because they were interesting. So age, huge age difference. So a mean of 62 in MET versus 70 for TZD is a standardized difference of a half, which is humongous. For CHF history, 6.5% versus just under 4%. For a 0.12, not terrible, but not great. CVD history, that's a typo there. That one's, I think it's about a 30 to a 23. This is about 23% here, or 0.16 on the standardized difference. A1C was fairly well balanced between the two, which was interesting, or at least was not so terribly imbalanced, but the percent of A1C observed, or the percent missing, was very different. And so about 34% versus 19%. A gimme, or a nice explanation for everything that we've seen up here, is this down here. So Medicare exposure was 47% versus 26%. And that exposure ends up being, we haven't dug into it completely, but a very probable explanation is this really is where they're getting their TZDs, that that it was easier to get the TZDs outside of the VA than inside. Now, not that there weren't people inside the VA getting them. A little more than half must at least half have to be VA users, because 53% had no Medicare exposure. Well, that's not exactly true. About 10% had Medicaid exposure, and so, but still, a big chunk is still getting them from the VA. The incident TX here, this is this 0.25 is based on all the years, but I focused in just on 2007, where we see start seeing a shift, as Christiane alluded to, into where concerns really started popping up. And then just file this one away in your memory for the moment. Statin percents, which is we'd really like to have well balanced, is perfectly balanced. It's actually 64% in both, and so file that away in your memory for the moment. Post-weighting, we see that, so here we've done the MET stabilized weight, and age ended up great, CHF, CVD, A1C, Medicare exposure, all of these ended up being pretty nicely controlled. Year didn't really benefit much at all. It went from a 0.25 to a 0.24. We really didn't get that under control at all with the weighting. And statins got a little bit worse. Not terribly worse, it's still less than 0.1. But in terms of variables you'd like to see balanced, it's sort of a shame that our weighting is imbalancing one of the ones that we would care about the most. If we look again at the completely unadjusted effect, so no weighting, no matching, no nothing, this is clearly our biased estimate. We have a hazard ratio of 2.56, a standard error on the log hazard scale, so this is the standard error of the beta, not the hazard ratio, of a 0.09 and super significant p-value. But we know that's biased. So just like before, just like with SOL versus MET, we have to do something to get that under control. So we have our weighted analysis, and this is what we get. we get a 1.38, so pulled that estimate way down, but our standard error exploded. We doubled our standard error. Now, we do expect our weighting to increase our standard error. There's no free lunch, and so weights are going to increase our standard error. Even though our true n stayed exactly the same, this weighted n has to be different because there's some price for including those weights. That's a pretty big price. We doubled our standard error. Now our estimate becomes not significant. That could be because this is getting pulled down or because that standard error is really huge, but it's certainly striking. The question is, what went wrong there? So what went wrong is that there's some really extreme weights if we look at those TZD weights. The mean weight for TZD is around 20. The maximum weight is around 1,000. And so there's people getting like 50 times as much weight as average. And so the question is, those extreme weights can really inflate our variance. When we pay a price for weights, we pay a big price for big weights. And so the really big weights inflate our variance a lot.
Again, it is similar to the old example when I said, well, you're putting in 3 SOL users who are younger to balance the net. Well, now we're putting in 1,000 TZD users who are 70 years old. And that is what caused that whole thing to look so terrible, really, because it just kind of blew up when you have 2 or 3 people who are so extreme in their weights. It's the equivalent of like adding 2,000 patients who look that extreme to your analysis.
And who are all identical. It's like taking one patient and just cloning them 1,000 times and throwing it in, and suddenly it becomes really volatile. Because you need, if you really had 1,000 individuals, you would get a lot of stabilization from it because there's a lot of information in 1,000 people. But when you take that one person and multiply them 1,000 times, you haven't added any information. You haven't gained any new information from that. You've just upweighted this one person in order to balance your covariate distribution. So the big debate that's been going on in how to deal with this is to truncate or to trim. Truncating is restricting the maximum weight to some value, say the 99th or the 95th percentile of the weights. There's no uniformly accepted practice in terms of this, and so whether you use the 99th or the 95th or something different is really up to you. A good reviewer will pick up on it and ask for sensitivity analyses for you to try different percentiles. The other camp argues for trimming, that is to remove subjects with weights greater than some value, say greater than the 99th or 95th percentile of weights. So this becomes an additional exclusion criteria, saying that anyone with a weight greater than the 95th percentile was removed from the analysis. With the thought process for truncating is, well, these big weights are blowing up our variance, and so let's just limit their impact by putting a cap on them. The idea here is, well, maybe these are weirdos, and so maybe the people getting really big weights are just weirdos. They're people getting something that they really weren't expected to get, and so we remove them from the analysis. So here's truncating at the 95th percentile. We get a hazard ratio of 1.61. Our standard error is a little bit better, and in this particular case, it happens to be better to the point of changing whether or not our estimate was significant or not. But we got improvement on our standard error, and that was the goal of the truncation. I have this 1.61 in red here, and the reason I have it in red is in terms of thinking of that estimate as biased or unbiased. What is that 1.61? Would it be biased or unbiased? Well, let me put it this way.
I will say that. That is a trick question.
I'll throw it in. If in order to get an unbiased estimate, we had to use this weighting here, what happens when we start taking some of those extreme weights and truncating how much they can influence the distribution? Well, we're not only changing how much they can impact the variance, but we're changing how well they balance the covariate distribution too. And so we're letting bias back in. We're essentially saying, by choosing how much to truncate, we're choosing essentially how much bias we're going to mitigate. And we end up kind of making a case for a bias-variance trade-off, that if we can let in a little bit of bias while getting a big gain in variance, maybe that's worth it. Maybe that's a trade-off worth to make. But it's notable that that's a biased estimate, that we're intentionally giving a biased estimate in order to get a better standard error. You can do the thought experiment of imagining what happens if you start truncating further and further, like rather than 95th, do the 75th and then the 50th percentile. So rather than truncating, this turned out that this was truncated at 70. So instead of truncating at 70, truncate at 50, then 40, 20, 10, 1. But once you're truncating down to 1, you're back to your no weighting cohort. Yeah.
Advantage to also truncating the lower end of the distribution?
It's a great question, and it's strange. It's not done, but there's a certain symmetry of thought in it that I like. And so the idea would be saying not let anybody get a weight lower than like the 5th percentile or something like that. And in terms of a bias variance trade-off, there's no real gain in working in the lower distribution, because those people who get really small weights don't impact our variance a whole lot, or at least they don't blow it up. Our variance goes up because we don't have, it's essentially kind of wiping those people out. So it's as somebody's weight gets really, really small, it's getting equivalent to almost dropping those people. And so they're not helping our standard error, but they're not hurting it in the way that the upper tail is.
So I imagine it's important to look at very carefully at the cases that are the really far outlying and try to figure out, I mean, maybe it's not maybe there's actual error in your data or something that's up, to figure that out first. I mean, to make sure that this is something real. I mean, it might be just fine, but I imagine looking at them very closely and trying to figure out, why does this person have such an outlying weight, and could it be for, a reason that is important to know or to understand?
Right, and that's a good point, that there can be something systematically going on up in that upper tail. It's probably worth noting in this case, truncating, we had 7,000 people, and so even truncating at the 99th percentile, we'd still have 700 of them. It'd still be a lot of them to look at. So truncation, we've allowed in some bias in order to improve our standard error. Let's see what happens when we do the trimming. So when we trim, our standard error gets again a little bit better, and I'll make the case that our bias is getting even worse. Why would that make sense? That in trimming, so now we made the case, we took these people who rather than truncating them at a weight of 70, we dropped them from our analysis.
I don't understand. What's the difference between these two?
So in the truncation, somebody who had a weight of 200 or 1,000, their weight just got set to 70.
Oh, okay.
So truncation truncated.
It's bigger bias because they're still contributing to you're not completely losing all information when you truncate, whereas you're losing all information that they could potentially provide when you trim.
Exactly. That's it.
So people stayed here without actually deleting this.
Right.
The left one trimmed means that you deleted it.
Exactly. We actually delete those people out. And so it's sort of like taking everybody who had a weight greater than 70 and setting their weight all the way to 0.
95.
Like just what? Yeah. So rather than bringing their weight down to the 95th percentile, we were bringing it all the way to 0. We're just wiping these people out, and so they're still they're not doing anything to help balance our covariate distribution anymore, and so our bias goes up.
So 5% of it is deleted basically.
Exactly, and it's 5% of the TZD users, because the MET users all have a weight of 1. So we can get a picture here of what's going on. This is another way to draw the propensity scores that I like. Rather than drawing the densities that we did before, this is an actual histogram of the frequencies. And so, of course, the MET users is the big bluish purple here, and the TZD users are the small red, just because there's so many more MET users than TZD users. And you can see that the TZD users are all over in this tail right here. And so there's just a few TZD users out along here. And so those sporadic TZD users here have to get upweighted to compensate for all of these people over on this end of the distribution. And so these TZD users end up having to get a ton of weight, whereas over here, these TZD users have weights pretty close to 1. Just have to upweight them a teeny bit to bring them up to the MET. Here, maybe a weight of 2. There's twice as many MET as SOL, but the ones down here are really having to get a ton of weight, and so it's down in this tail where our headache is occurring, and where there's just a very few, if any, TZD users. So what is the solution that we can do? We could stabilize by TZD instead of stabilizing by MET. And so rather than trying to shift the TZD users and upweighting them to look like the MET distribution, we can shrink the MET users down. We can downweight all these MET users to fit the distribution of the TZD users. And an advantage of that is it takes this tail and essentially just shrinks it down to 0, to an insignificant value. Whereas these, this just needs to get shrunk down to there, that needs to get shrunk down to there, and then this long tail pretty much disappears. And so the TZD users are all going to get a weight of 1, and the MET users are now going to get a weight of something less than 1. Or
This is the ATC method kind of?
Yes, you could think of it as the ATC. So if ATT weighting is the average treatment effect among the treated meaning MET, then the ATC weighting would be the average treatment effect among the controls or among TZD users. And exactly, so like ATC, kind of referring to the distribution that we're standardizing to, or the population that we're standardizing to.
Does it make sense to select as your treated group the group that covers more parameter space, or even because the group I forget which one it was, but the larger group completely covers the distribution of the one, whereas the other one there's practically only covers. I mean, I know there's sparse cases. Does it make sense to select it that way? Is that
yes?
Okay.
And in fact, it's a great point. And so the question is, does it make sense to pick this as the distribution we're standardizing to? And I think absolutely, because it's the one that we can answer the question for. So this average treatment effect among the controls, or among the TZD users, is something we can estimate because we have so many MET users that for any kind of TZD user, we have some MET users who look like that. But the converse isn't true. To know what the average treatment effect of TZD is among MET users is a really hard quantity to estimate, because we have MET users for whom there's no TZD users out there that look like them. And so to say that we want to, even though we can just rush ahead and do the ATT weighting to scale it to MET, which we wanted to because that's what the that's what we had done in our first analysis, we don't have the data for it. We don't have TZD users who look like all of our MET users. That's not it's just the ATT is not a quantity we can estimate very easily with this data set. As opposed to the ATC, the average treatment effect among TZD users, that we can estimate in spades. because that we're well positioned to estimate because we have such an abundance of met users. And so I really like this as the best estimate. It's nice that these two ended up agreeing pretty well in terms of the point estimate, which is encouraging. They don't have to, and they're estimating slightly different things. This is estimating the ATT, this is estimating the ATC. The key thing to note, though, is that variance is fantastic. That the standard error for a point estimate, we paid just a teeny price. And the reason why we paid just such a teeny price is because our weight for our met users are all between 0 and 1. And so there's no explosion of weights that we have to worry about. There is a question of what happens if we don't have one group completely dominating the other group? What are we going to do? Like maybe this could have the TZD users could go off like this, where there's a bunch of TZD users who have no met users looking for them. There's a really nice solution by Lee and Green, who propose what my student Laurie Samuels is doing some of the causal inference theory behind it, and she's referring it to as ATM weights, or the average treatment effect among a matchable cohort. And so if we think of what matching does, matching takes individuals and matches them to other individuals one-to-one as best as it can. And so out of this chunk here, it's going to select an equal number of met users to match to them. That's equivalent to down-weighting that group there. Whereas if there's a group of TZD users over here with very few met users, it would downweight the TZD users in order to pull them in. So the matching essentially downweights whatever group is in the dominance. Whatever group is more prevalent is going to be what gets downweighted. That's what matching does. And so Lee and Green came up with a way to do that via weighting, where they stabilize by the minimum of the propensity score and 1 minus the propensity score. And so if you think about the propensity score as a number between 0 and 1, this minimum is always going to be something less than 0.5. It's essentially taking whatever group is in the minority or at a given spot in the propensity score space and stabilize by that. So over here, we would be stabilizing by TZD all the way over in this tail. But if TZDs blew up over here, then we'd end up stabilizing by met. We end up stabilizing by whatever group is in the minority. And what that does is it takes a tail like this, and that numerator is essentially going to 0. And so wherever there's an overabundance of a certain distribution, that it essentially wipes out that tail. And so these ATM weights can wipe out the tail. Now in this case, because the metformin dominated everything, the ATM weights and the ATC weights, as we're calling them, just end up being the same thing.
If they are not overlaid like this way, then basically it will be this ATM should be the kind of between ATT and ATC.
Exactly, exactly. And so it has nice properties there. So I'll finish up just by talking about the reminding ourselves of the assumptions of the propensity score. That there's assumption number 1 is no unmeasured confounders, where we do the best we can, but sometimes that's more true than others. When you have 45 good covariates, that's much more true than when you have 6 covariates. Or 45 lousy covariates. And so number 1 is never completely true, but sometimes it's much more true than others. Number 2 is positivity, this idea of overlap in the covariate space. Unfortunately, we tend to treat positivity as a theoretical exercise sometimes, that we think, as stated, it's everywhere in the covariate space there is a non-zero probability of both exposures. And so for any set of covariates, you have to have at least some probability of being exposed. Now, often we play a theoretical game and think, well, yeah, that's true, in theory, and I like to think about the fact that, at least in America, we cannot estimate the effect of smoking on 2-year-olds. Now, it doesn't mean in theory there's no smoking 2-year-olds, but in any data set we have, we don't have smoking 2-year-olds. And so we could build a model. We could, if we included 2-year-olds in our analyses of smoking in there with our teenagers and our adults, our model would extrapolate away, and it would give us an estimate for the impact of smoking in 2-year-olds. But that estimate would be ridiculous because it would be based on smoking teenagers and adults and non-smoking teenagers, adults, and toddlers. That there's a region of the covariate space where there's non-positivity. And so the data has to be there. They're just, in order to get an estimate for the exposure effect, there has to be both exposed and unexposed in the data that you're working with. Now, to finish on a happy note, I'm happy to say I've read that this sweet little boy here has since quit, and so he is now a former smoker.
I really have this like the meme of the related to your next point. If go back to your histogram there, if there is no overlapping region, like the one histogram here and another group is this way, and there is some non-overlapping region on both sides, until ATM method would work.
So if the propensity scores don't overlap at all, like
still overlap.
Oh, okay.
But some tails both sides.
Yes.
Not overlap at all. For example.
Yes.
Then
so if you had like, if you had say like a really heavy tail of met users here and a really heavy tail of here,
so nothing actually. The only one group is dominated for each side.
Exactly. Then the ATM works great. That's actually, the ATM, because what the ATM ends up doing is it ends up essentially zeroing out both tails. And so it reduces to the range where there's overlap.
That still would be not good for some outliers, because it's heavy tails have big values.
And it's true that they have the potential to create big values, but that numerator goes to 0. And so because the numerator is the minimum of the propensity score and 1 minus the propensity score, and so that thing that we stabilize by goes to 0, provided the propensity score model is flexible enough. And so if we fit a really crude propensity score that is forcing positive values onto TZD users where there's no real TZD users present, then that can lead to bias. We can still have a biased estimate there because we're not zeroing out our exposed people where there's no unexposed people. And so we do need a sufficiently flexible propensity score model in order to be able to handle those situations well. Which is actually a nice point in that the nice fallback is if we're in a really severe situation, it's worth going back to our inclusion-exclusion criteria to get a sense of what's driving that. Because it might be we just picked bad inclusion-exclusion criteria. We need to tighten, say, our A1C criteria or something in order to be able to shrink those tails via pruning. Okay. Cool. All right, well, thank you, everyone.
Package I use for propensity scoring, they use the treated groups standard deviation in the standardized estimate score. I never thought to check that, but they're assuming just homogeneity of variance, I guess.
Or that's interesting. They just picked one of the groups.
They just picked one. That's an odd thing to do, but I never thought to check that.
Cool. And thanks to everyone online.